Hi folks, it's Dr. P. This video is going to get you acquainted with the register adder that's built in Lab 12. This is the only circuit in Lab 12, so it's important to be able to really understand it so that you can finish in our 3-hour lab session. It's also going to be crucial to break it into parts so that you can build it in stages rather than trying to do all of it at once. The lab manual contains a lot of really good information. Read it and reread it. There's a block diagram that can be used to help track inputs and outputs for different devices. This is like having a zoomed out view of what you're going to build. The actual schematics are up to you. What I'm going to do is build this circuit and discuss it as I complete each stage. The first stage will be to build the finite state machine and control logic. The second stage will be to get the adder to actually add and store those values. The third and final stage will be to implement reset and overflow clearing logic. Ready? Let's do it. I've now built the control logic for the registers. This is just a finite state machine that will be used to create control signals for the two registers. For now, all I want to do is make sure that the state machine progresses through the correct states. The reset state, which is 0, 0, should be happening all the time until I press the load button, which is this button right here. As soon as I press this load button, it's going to be asserting both of the preset pins and put the state machine into state 1, 1, which is state A. On a rising edge, the state machine will go to state B, which should be 0, 1, and then on the next rising edge back to reset, where it'll stay until I asynchronously press this button. So I'm going to do it, and we see we get 1, 1, 0, 1, and then back to 0, 0 again. I have the clock set pretty slow. This is the clock signal. Later I'll increase the clock speed, but for now I just want to be able to physically track that progression from state A to B back to reset. For now I'm completely ignoring those clear pins on the flip-flops. I'm not worried about any type of overflow logic or resetting logic yet. I'm also not worried about actually adding numbers together. I'll deal with that next. So now that I know that the state machine works, I can generate state machine outputs, which are then the control signals for each of the registers, and make sure that those work as well. So what I'm looking for now that I've built the control signals, they're just more machine outputs. I should check that both of the outputs are 0 in the reset state, which they are. And then I'm going to have one of the outputs be 1 in state A, the other output is 1 in state B, and then they go back to zeros again. So now we have all of the control logic completely done, and now we can start thinking about other parts of the circuit, like now let's get this thing to add. Okay, now this thing can add. So just do a couple of examples. Put my input as 2. Click on load, and 6 and 3 and so on. Totally works. So the control signals that I created before go into the S0, S1 pins of each of the registers. There is a lot of feedback going on in that, outputs are inputs and inputs are outputs. So you really have to keep track of things, and it can be tricky to do that. I labeled both of my registers, and I used blocks of different color wires to keep things separated. Like I used my dip switch has white wires, and my output has yellow wires, and this register, which goes to the old sum outputs, which go to the one of the inputs on the adder are green wires, and then the outputs from the adder into both of the registers are brown wires. So that really helps. I also had my data sheets really close to hand. I had my logic probe, which I used a lot, and I wrote things down. Specifically, I wanted to keep track of my MSBs and LSBs for each signal. For the adder, it matters which signal is the MSB. A4, B4, and sigma 4 are the MSBs, right? So that's dictated by the data sheet. For the registers, it doesn't really matter. So I chose A as my MSB for both of the registers, and then D was the LSB, and I just kind of stuck with that. Now I have evidence that this thing can add, so that's really good news. The only thing I need to do now is put in the overflow and clear logic, because right now weird things happen if I try to add 5 to 12, and I'm going to get like a weird result, right? Like 1 doesn't make sense here. So what we need to do is find a way to clear this thing out if it's going to overflow. And also, I'd like to just be able to clear it. Right now, I'd have to unplug it, or I'd have to keep adding over and over and over again until I eventually get to 16, which is this thing's other way of clearing itself out. Okay, so now the register adder is finally working. So we've got all 3 components now kind of together. We have the control logic that does the hold or load for both of the registers. We have the adder, so we can actually add things. And we also have the reset logic. So now that everything's together, how do I know that this works? So firstly, when I load, I should be able to get numbers that sum together. So what we should see is anytime there's going to be that overflow, right? 14 plus 3 shouldn't be able to fit. If I press that load button, it will go to 0. Of course, I can also load and hit the reset button, and that's also going to reset things. Okay, but we also have that overflow protection now, so we can keep adding numbers. And again, 12 plus 5, this should overflow, and it's going to reset itself. Okay, so this now meets all of the functionality that I've requested. It can add numbers, and at a certain point, if the output is going to overflow, it will reset itself. Additionally, the user can reset it at any point by pressing the clear button. All right, folks, hopefully that helps to demystify this circuit. Now you know how to build it, you know how to break it down into pieces, and you know how to check to make sure that it works. Until next time, stay well.